In this video, we're going to conclude our discussion of conservation of momentum. We're going to look at two additional topics, the concept of impulse, and we'll look at two-dimensional collisions. So let's look at where the concept of impulse comes from. Basically, what I want you to understand is where this equation comes from. So we're going to start with Newton's second law. We know that Newton's second law tells us that the net force is equal to the rate of change of the momentum with respect to time. Now, most of you who are taking this course are in Calculus 1, so I don't expect you to understand the details of what I'm about to show you, because it's really something you learn in Calculus 2. But it turns out that you can take a derivative like dp dt and split it and rewrite the equation this way, and then you can integrate both sides. When we integrate dp, we just get the final momentum minus the initial. In other words, this becomes delta p. The right-hand side, the integral of f dt, we're just going to keep like this for a moment. Now, again, I don't expect you to know how to integrate if you're in Calc 1 because you haven't learned it yet. But what I do expect you to know is the meaning of an integral. This is something we talked about in an earlier video. Remember that an integral of a function is simply equal to the area under the function. So if I've got a function that looks like this, and I take the integral of f dt, then what that is equal to is simply the area under that function. Okay? So the area is equal to that integral. Okay. So what is this whole idea? What are we trying to accomplish? Think about an object that undergoes a collision. So let's say we throw a ball against a wall, and the ball is going to hit the wall and bounce off. As that collision is occurring, the force on the ball is going to vary with time. In other words, just when the ball starts touching, the force will still be 0. It will probably then increase to some maximum amount, and then it will decrease as the ball moves away in the opposite direction. So that's what I'm trying to represent with this graph. That would be looking at what the force is on an object during a collision. So what we've learned is that the change in momentum of our ball as it hits the wall is just equal to the area under the force versus time graph. That's what this equation is telling you. Now, it turns out that often we don't really know the details of what the force looks like over time. In other words, we don't have this information here. So what we do is we come up with kind of an equivalent way to look at it, which is to say, what was the average force acting during the time of the collision? So in other words, the time of the collision, delta t, is just the time over which there was a force. What we do is we say, well, what would the average force be during that collision? And what we really mean by that is that the area here is equal to the area here. So in other words, if we had that average force acting over the same amount of time of the collision delta t, it would provide the same impulse. Okay? So that's how we end up with this equation. It's often referred to as the impulse momentum equation. The average force of the collision times the time of the collision, that is what we mean by the impulse. So the change in momentum is equal to the impulse. You'll notice really after all that work, it's simply just a different way to state Newton's second law. Look at the following question. Which experiences a greater force, a piece of clay thrown against a wall or a metal ball thrown against a wall with the same initial velocity? And assume that they each have the same mass. Go ahead and pause the video and think about this. Okay, so when I ask this question in a classroom environment, usually the answer that's most common is C. But that's not right. And usually when students answer that, I ask them the following question. I say, would you rather have me throw a metal ball at your head or a clay ball at your head at the same velocity? Well, everybody immediately knows that obviously you don't want either to happen, but you'd rather be hit with the clay ball than with a metal ball. Well, why is that? It's because the metal ball is going to exert a greater force on you, and therefore you're exerting a greater force on the metal ball to stop it. In order to understand this question, we want to use this concept of impulse and change in momentum. So we know that delta P is equal to F delta T. And you'll notice here I have both the vector sign and the average sign on the force. Well, we can obviously rewrite that for the average force as delta P over delta T. And what we see here is that what's going to govern the force that an object experiences in a collision is how much the momentum changes and over what time does the collision occur. So now let's think about what happens when a metal ball gets thrown off a wall. Well, first of all, metal is obviously not compressible. And so when that metal ball hits the wall, a couple important things happen. First of all, the metal ball bounces off, and it probably will bounce off, if it's a good hard wall, it's going to bounce off with almost the same speed that it came in with. So the change in momentum, we had momentum in this direction, now we've got momentum in this direction. That's a big change in momentum. So the metal ball has a bigger delta P. Because think about what happens with the clay ball. If you throw the clay ball, it hits the wall, probably just, it might stick or just kind of thump and hardly come back at all. So the clay ball loses this momentum, but it doesn't gain momentum in the opposite direction. And so the metal ball has a greater change in momentum. The other thing, though, is that because the metal ball doesn't compress, the collision takes place over a very short amount of time. So delta T is shorter for the metal ball. The clay collision takes longer because when the clay first starts to contact to when it stops, that's a longer period as that piece of clay kind of mushes against the wall. And therefore, you'll notice that the wall has to exert a much bigger force on the metal ball than it does on the clay ball. And therefore, the metal ball exerts a much greater force on the wall than the clay ball. And that's why you'd rather be hit with a clay ball than a metal ball. We can also use the impulse momentum equation to think about why airbags are a great thing to have inside a car. So if you don't have an airbag, and especially if you don't have your seatbelt on, in a collision, if you're the driver, what might happen is your head bounces off the steering wheel. Well, that's going to be a big change in momentum, and that collision between your head and the steering wheel is going to take a very, very short amount of time. However, when an airbag deploys, it's going to lessen delta P because your head is not going to bounce back as forcefully as it would if it hit the steering wheel. It's also going to lengthen the time of the collision, and therefore there's going to be less force experienced by your head in that collision. Go ahead and pause the video after I read this question and go ahead and see if you can get the correct answer on your own. A ball with a mass of 0.2 kilograms is thrown at a wall with an initial velocity of 30 meters per second. It bounces off the wall with a speed of 20 meters per second. Assuming that the collision took 0.010 seconds, what was the average force exerted by the wall on the ball? So go ahead and try that on your own. Okay, let's see how you did. So we're using the impulse momentum equation. We have the average force times delta T is equal to the change in momentum. The vector signs on this formula are important because we got to pay attention to direction. So just to draw what's going on here, here's the wall. our initial velocity, VI, is 30 meters per second. And we can see it's in that direction. Notice, by the way, I told you that it bounces off with a speed of 20. Hopefully you realize that that means that as that ball comes back off the wall, its final velocity is negative 20 meters per second. Okay, so now we just need to solve it. So the average force is equal to the change in momentum divided by delta t. And delta p is just the final momentum minus the initial momentum divided by delta t. When we plug in the values, notice that because the object bounced back, we get negative 20 for our final velocity there. And our initial velocity was positive, but it's negative, so that's also ends up being a negative term. And that's important because what you'll notice is that both of those terms are negative. In other words, we get a bigger force because the object bounced back versus if it hadn't bounced back at all. If we take that now and divide by the time of 0.010 seconds, what you find is that the force is negative 1,000 newtons. So again, that negative sign simply implies that the force that the wall exerted on the ball was to the left. Let's take a look at how we solve two-dimensional collisions. We know that momentum is conserved in every collision. In other words, we know that the total momentum before the collision is equal to the total momentum after the collision. But how do we deal with problems that involve two dimensions? Well, we deal with it just the way we always deal with vectors, and that is we break things into components. So if overall the initial momentum has to be equal to the final momentum, well then that has to be true for each component. In other words, the total momentum initially in the x direction has to be equal to the total momentum after the collision in the x direction. And again, I'm using capital P there to represent the total momentum. It also has to be true in the y direction. PIY has to be equal to PFY. So when we're doing problems with two-dimensional collisions, it really just comes down to working with each component. So let's look at the following example. A billiard ball moving at 2 meters per second strikes an identical ball and the balls move off as shown. What's the final velocity of the two balls? So there's one other piece of information that I'm going to give you in this problem, and that is that both theta 1 and theta 2 are 45 degrees. So theta 1 is 45, theta 2 we'll write as negative 45 degrees. So those angles are both the same. What we want to do then is simply write down what's the momentum before and after. Notice that, and by the way, this is a top view, so you can picture like, balls on a pool table if you want to. So when object 1 comes in and hits object 2, object 1 we can see goes off in the upward direction, object 2 goes below the x-axis. So initially, object 2 is at rest, and only object 1 is moving, and notice it's only moving in the x direction. Therefore, our initial momentum in the x direction is m1 v1 initial. In the y direction, there is no momentum initially, so that's just 0. After the collision, we now want just the components of the momentum in the x direction. So we've got m1 v1 final and m2 v2 final for the two final momentums. But we only want the components. So in other words, we have m1 v1 final times the cosine of theta 1 and m2 v2 final times the cosine of theta 2. Now let's go ahead and look at the y direction. So again, the momentum initially in the y direction is 0. After the collision, object 1 has a momentum m1 v1 final, but we only want the y component. So we're going to write sine theta 1, and then m2 v2 final, and then the sine of theta 2. Now, you might have said, shouldn't this be negative? And the reason I'm not going to put a negative sign in there is that I am treating this angle as negative. So when I take the sine of negative 45 degrees, this whole thing will be negative as we expect. So that's why I'm not putting in a minus sign by hand there. Okay, so that's really the physics of two-dimensional collisions. We just write down conservation of momentum separately for the x and the y components. At this point then, we would just need to go ahead and solve. So let's do that. Notice that in this particular problem, the balls are identical, and therefore m1 and m2 are the same, so I can get rid of the m's in both equations. If I now look at the y direction, you'll notice that I can rewrite this as v1 final is equal to negative v2 final sine theta 2 over sine theta 1. But since theta 1 and theta 2 are the same angle with just a different sign, you'll notice that what that simplifies to is v1 final is equal to v2 final. Now, of course, that has to be true here. If the balls are identical and they go off at identical angles, the only way that the y component of the momentum could cancel out is if they have the same magnitude of velocity. Once I have that, I can go back over to this equation. We have v1 initial is equal to v1 final cosine theta 1 plus v2 final cosine theta 2. And I'm going to rewrite that. I know that v1 and final and v2 final are the same now. So I also know that the cosine of negative theta is the same as the cosine of theta. And therefore I can see that these two terms are identical. So I get v1 initial is just equal to 2 v1 final cosine theta 1. Or v1 final is v1 initial divided by 2 cosine theta 1. If you plug in the values, you should get 1.4 meters per second. And so both v1 final and v2 final are equal to 1.4 meters per second. Let's look at a second problem. A billiard ball of mass 0.4 kilograms moving with a speed of 1.8 meters per second strikes a second ball initially at rest with the same mass. After the collision, the first ball is deflected off at an angle of 30 degrees with a speed of 1.1 meters per second. Find the final speed and direction of the second ball. So I'd like you to try this on your own, but let's first just draw the diagram together to make sure that we understand what's going on. So very similar to the last question, we've got our first object coming in, and it's going to collide with object 2, which is initially at rest. After the collision, object 1 is going to go off at an angle of 30 degrees. So theta 1 is 30 degrees. And it's going off with a velocity, v1 final of 1.1 meters per second. Object number 2 is going off at some final velocity that we don't know at some angle that we don't know. So why don't you go ahead and see if you can solve this problem. Again, you want to start with the fact that pix is equal to pfx and piy is equal to pfy. So those are your starting points. Okay, let's go through this together. So again, here's our picture of what's happening in the collision. Object 1 is coming in with an initial velocity of 1.8 meters per second. Object 2 is initially at rest, so I'll just add that here. v2 initial is 0. And then we know what happens with object 1. We know its final velocity in the direction it goes off in, but what we're looking for is what happens to object 2. What's the magnitude and direction of its final velocity? So those are the things we're trying to find. Again, in a problem like this, we always want to now start out with conservation of momentum in each component. So pix is equal to pfx. And let's go ahead and write that out. Before the collision, only object 1 is moving, and it's moving entirely in the x direction. So we'd have m1 v1 initial. That's equal to m1 v1 final. So that's the final momentum of object 1. But again, we only want the x component of that. So I've got to put in cosine theta 1. And then the same thing for object 2. m2 v2 final cosine theta 2. Okay, so that's what momentum, conservation of momentum looks like in the x direction. In the y direction, we have piy is equal to pfy. There is no initial momentum in the y direction. After the collision, object 1 has momentum m1 v1 final sine theta 1, and then object 2 has momentum m2 v2 final sine theta 2. And again, I'm putting plus here. The fact that that term overall is going to be minus comes from the fact that theta 2 is going to be minus, and so that should come out of my solution. Okay, those are our two equations. So now the way I solved this problem was I first rewrote both equations, and the first thing I did was, since m1 again is equal to m2 in this example, I can get rid of the masses in both equations. Then I took each of these and solved for what I don't know. I don't know v2 final, and I don't know cosine theta 2. So that's equal to v1 initial minus v1 final cosine theta 1. Do the same thing for this equation. v2 final sine theta 2 is equal to negative v1 final sine theta 1. Now, one of the things that you'll notice here is that I've got two equations and two unknowns, right? So we're in our kind of standard math situation where we've got two equations and they're two unknowns. We don't know v2 final, we don't know theta 2. There's kind of a clever way to solve for this, and that is by dividing the two equations. Notice how that works. I'm going to take this equation and divide by this one. So I get v2 final sine theta 2 divided by v2 final cosine theta 2. So that's what I get on the left. And on the right, I get negative v1 final sine theta 1 divided by v1 initial minus v1 final cosine theta 1. Well, the reason that that's kind of a good way to do it is you'll notice everything on the right we know. On the left, the v2 finals cancel out. And what's sine divided by cosine? It's tangent. So in other words, I get the tangent of theta 2 is equal to all this stuff. And you can just go ahead and plug in to figure out what that value is. I'm just going to shortcut it here. You should try this on your own. Make sure that you can get it yourself. What that worked out to be for me was negative 0.649. Therefore, theta 2 is the inverse tangent of negative 0.649. And what I ended up with then for theta 2 was negative 33 degrees. Notice that that makes sense. We know that it's got to be negative, and it's probably not too different from theta 1, so that certainly seems like a reasonable value. Once I've solved for theta 2, I can go back to either equation to solve for V2 final. In other words, probably the easier one is this one. I know that V2 final is equal to negative V1 final sine theta 1 divided by sine theta 2. And once again, you now know everything on the right-hand side of the equation. Go ahead and try it on your own. What I got for V2 final was 1.01 meters per second. Okay, so again, just to review, when we're doing a two-dimensional collision problem, it all comes down to making sure that momentum is conserved in both the x and the y component. And after that, and after you get to that next step, then it's really just the mathematics of two equations and two unknowns. Okay, that ends our study of conservation of momentum.